Welcome back to Chapter 9. Chapter 9 is the final chapter in our Unit 2. It's also possibly the most math intensive, possibly the most math intensive chapter of the entire year. It also is the possibly least important because it is barely touched upon, if any, on the AP test or anything like that. We do need to cover it, but it is not something that um, that you need to be really good at to be successful here. And so what we're going to be doing is we're going to be re-expressing the data to straighten it out. We want to make things linear if they're not. So how do we make things linear? Now we can't use linear transformations like stretches and translations. That doesn't do that. That retains the shape. We have to do something different. So we're going to see some different options. So we can't use a linear model unless it is linear, right? That's one of the things. And so we re-express it to make it linear. Two simple ways are using either logarithms or reciprocals. And then re-expression can be seen in everyday life, and everybody does it. So logarithms, reciprocals, also squaring or square rooting things can help as well. So here we have the relationship between fuel economy in miles per gallon and weight in pounds. And it looks pretty linear. Looks like we can have a line, well, except that here there's another line. So maybe this doesn't look linear. And if we look at the residuals, we can definitely see this curve in that residual plot. So we're going to have to do something else to straighten it out. So here we have predicted miles per gallon and the residual mile per gallon. So what we could do here is we can use the reciprocal. So instead of doing the miles per gallon in the original, so we have the original had the weight down here and then miles per gallon, but instead of miles per gallon, what if we went gallons per, not gallons per mile because that's a really small number, do gallons per 100 miles, just so that it's in the integer range instead of 0.03 to 0.06. So this is basically 1 over y. And now look, it's nice and straight. It's got a good straight line going to it. And so just by flipping over the y value, we were able to straighten that. And then we can do a linear regression. The residuals from this one, we have our line there at 0, a nice scatter right about the line, perfectly what we're looking for residuals. And so when we're re-expressing stuff, or when we need to, we do have a few different goals that we're trying to get. Trying to make things more symmetric, because if it's symmetric, that means it's going to be closer to normal. And that's a big thing, because when the data is normal, or approximately normal, because it's never going to be normal. When it's approximately normal, when we can use the normal curve, that allows us to do a lot more stuff with it. So if we can get it to be there, we can. And so what they did here to do it, notice the y values are the same as the number of companies, but in the x's, they took the log of the x's. So that would be probably the natural log. Perhaps the log, it doesn't matter. It'll do the same thing. But the log of the x values. And that made this data much more symmetric. Goal 2, make the spread of several groups more alike, even if their centers are different. So here we have some pretty big spreads and super small spreads here. Over here, they're all about the same. I mean, they're always going to be different, but they're closer. And so in this case, they left the x's alone, but we have log of y. So the x compared to the log y graph here made it so that spreads were about the same. to make a scatter plot more linear. What we can do is take the log of x or y. In this case, we have log of x in both, so the x's there didn't change. But this is log of y. And what it did was it brought these guys up to make it way more linear so that we can get a regression line there. Like this one, this first one, I mean, it's going to kind of be curve-ish, but even still, that's no good. And we don't want to use those curved regression things that you've used in previous classes. They're great for that, but when we get to statistics, we want to keep things linear, and we'll explain why in a second. A different goal, same thing. When we took the log, in addition to making it straight, it made the variation pretty much the same around the whole thing. Instead of being super thick right down here and then spreading out over there. So in addition to making it linear, it put our variation together so that we get a good model to do a regression on. So how do we do this? How could you think about, like, well, what do I have to do? Sometimes what you have to do is simply just trial and error. Try something. If it doesn't work, no big deal. Try something different. But here's some things that you can try. So it's called the ladder of powers, and it's looking at what the effects it wants to do re-expression on the data. So a second power, you square the data powers. And then they say try it with unimodal distributions or skewed to the left. So if it's skewed to the left and you want to unskew it, square the data values, see what happens. The power of 1 is just the raw data. So that's if it's basically linear. It has positive and negative values. So that makes it so you can't do some stuff like logs and square roots and stuff like that. You can't have negatives. You can always do a horizontal translation or possibly even a vertical translation to get rid of the negatives, but still. A half power, that's a square root. So if you, it says the counts often benefit that. If you have a count of something, you can take the square root of x or y, and a lot of times that will help to linearize it if it's not already linear. And if it looks like it's squared, a square root would get rid of a squared. So, I mean, you can use inverse operations to try to make this happen as well. The zero power, it's like logarithms, we'll get there because depending on what kind of logarithm you take, or depending on where you take the logarithm, you get different types of equations. The negative 1/2, it's a reciprocal square root. It says it's uncommon. I've never actually seen that one used, but who knows, maybe. And then the negative 1 is the reciprocal. And so when you have ratios, like miles per hour, we flipped it to be hours per, or no, we had miles per gallon. We flipped it to be gallons per mile or 100 miles. And so you can deal with that, especially like the reciprocal. If you remember the graph, it kind of had a curve like that. That helped that curve. So that's when you would want to do a reciprocal. So logarithms. First of all, none of the data can be 0 or negative. You can't have that. You can do again, a translation or two to make it so that everything's positive, but you can. And so you can take logs of x, the x variable, the y variable, or both, and graph them. So you could do log of x and y, graph it. Is it linear? No. All right. x and log of y, graph it. Is it linear? No. All right, log of x, log of y, graph it. Is it linear? And so you can try all three different combinations there. That's what that last one says too. And so this is the type of deal you get. If you had an exponential function, x and log y will linearize an exponential function. A logarithmic function, log x and y, will linearize that. And then a power function, if you take the log of both of them, that linearizes that. And a power function is y equals ax to a power. So a quadratic would be a power function. As long as there's no extra variables in there, like no like plus 3x plus 2. Just y equals 2x squared. It's a power function. Y equals square root of x. It's a power function because that's x to the 1/2. The nice thing about this power function is, like, maybe squared doesn't quite fit and maybe cubic doesn't quite fit, but it's in between. The power function will get you an exponent like 2.5. It'll get your exponent will be way more precise. Now, if you got an exponent of like 1.99, chances are I would just go with a squared on that one because it's not going to fit perfectly anyway. But if it's basically something, or you get like that 0.499, that sounds like a 0.5. That's a square root. But if you get like 0.783, all right, just go x to the 0.783. That works. And that's when you have log x and log y. You graph the log of both of them, you get a straight line. That's going to get you a power function. And then you would do the regression with whatever. Like if you have log x and log y, and that makes a straight line, do your linear regression with log x and log y. You get your regression. And then when you write your equation, it's a little bit different because it's not y hat, it's log y hat would equal the slope times log x plus 1. So you do need to include the log or whatever kind of transformation you did. You need to include that in your equation. So if you took the square root of the x's and matched them with the y's, you'd have y equals a times root x plus b. And so we often choose the re-expression for one reason, and then we find it has other things. So, for example, the scatterplot we saw where they took the logs and it made it linear, it also pulled the variation in so that the variation was pretty much consistent throughout. Also, if you do something that makes the histogram more symmetric, it may also straighten the scatterplot or stabilize variations. So those are some of the goals that we're looking for there. And then it's like, well, why not just use a curve? In Algebra 2 and in pre-calc, we learned it's like, hey, you can do quadratic regression, you can do cubic regression, you can do power exponential regression, you can do all sorts of different kinds of regression. So why not just use the curve for that? And the answer is because they're way more difficult than lines of best fit, first of all, like for the calculation part, and they tend to not be quite as accurate. But also with lines, one of the things that we did with lines was we had to interpret the slope and the y-intercept. Those have meaning. Once you get equations that aren't lines, you lose that meaning. So you get that. And besides, the correlation is it's specifically how well it matches a straight line. And so if you have a different type of a model, the correlation doesn't really fit as well. So what can go wrong? Things can go wrong. This would be just using the types of regression in the calculator. Transform the data first. You will actually get different equations most of the time. Don't expect your model to be perfect. You never expect your model to be perfect. There's going to be outliers everywhere. It's not going to fall in a straight line. We use real world data. This isn't Algebra 1 or even Algebra 2 where the points came basically from an equation. You plug in the values, you get the points, and then you come back with the equation. These are real world data, and I mean, it's going to be spread out. It's not going to be perfect. Um, don't go too far from the ladder. Like, don't get up into like the cubes and stuff like that. Um, it just, if it's too complicated, it's probably not working right. And then don't choose the model based on the R squared alone. That can help you pick, but you also need to be looking at the model, like actually having eyes on it, looking at it. Does it make sense? Um, means more than an R squared a lot of times. And sometimes you might um, you might uh, know something about it anyway. If we're looking at like an area of a circle, something like area of a pizza, well, the area is pi r squared. So chances are it will be proportional to the radius squared. And so if I graph the radius and the area, it's not going to be straight. But if I graph the radius squared in the area, it has a way better chance of being straight. Um, More what can go wrong. Beware of multiple modes. Um, there's nothing that's going to help with multiple modes. We can fix skewedness, but if there's a couple modes, that becomes problematic. And that's when you have to look to see if maybe you have two populations that you want to separate. Um, and then watch out for scatterplots that turn around. All of our stuff can help fix curves, but not stuff that actually changes direction. So if it's not monotonic, it won't help. Monotonic means it's either always increasing or always decreasing. So this one increases and then it decreases. We're not going to be able to fix that. And then over here, even it decreases, then increases. Not going to be able to fix that either. So it can help us when we had like curves that look like that. It can help when we have curves that look kind of like that. Um, so we can do a lot with curves, but not when it actually changes direction. And then watch out for negative data values. It is possible that some of the stuff that you might collect has negative data values. You can't do logs or anything or roots with those. So um, you can do a translation and then deal with it, but hopefully you don't have to. So what have you learned? So when the conditions are not met, like it's not linear, we can do a re-expression, possibly, and that might help. It can make the variable more symmetric if we're looking at a histogram. It can help to fix the spread to make it all kind of more even if we're looking at a scatter plot or side-by-side bar graphs. And can make a scatter plot straighter, and it can make the scatter around the line, which is actually very similar to that. Similar, not exact, but similar. Um, Taking logs is a good way, it's a good starting point. Um, and then the ladder power log approach is good place to start at least. Models won't be perfect, but they'll be useful. Some AP tips. Um, so it's not really on the test. A little bit like knowing some concepts, but not actually doing the stuff. So tips for this, make sure you can make accurate predictions using a transform equation. So if we have like log y and x, you plug in x, you get a value. That's the log of the value. You have to get the actual value from that. Make sure your descriptions use the transform variable names, not the original variable. So we'd have like log of weight, because log of weight in something is going to be linear. And then don't get lost in the technology. You won't have to do this, but they just might give you some output or give you the data, and you just have to answer a question about that. So don't get too bogged down in the process. I'll show you how you can do it, but you just make one of your columns as log of x and log of y, and then you can start graphing different stuff to see what makes it straight. So with that, I'll see you later. But until then, keep working problems, keep asking questions, and as always, happy mathing.